In our previous video, we began studying the water hammer phenomenon which occurs in closed pipes during transient conditions. As we saw, it can happen during the closure of a valve, when the closure time is too small, and in pumped lines when a power failure occurs. We saw that when water flows in an installation like this, if the valve is closed instantaneously, these transient pressures or transient heads will start to form. But we said that if we close the valve more slowly, we can alleviate these transient pressures in a certain extension of the pipeline. But first, let me introduce myself. My name is Marcus. I'm a retired professor of hydraulics. Now I'm a consultant engineer of many companies that deal with hydraulics applied to sanitation works. Okay, this is the initial condition. Here we can see the water flowing in steady flow. Just to remember, U0 is the average water velocity in the steady flow condition, and A is the celerity of the transient pressure waves. Now, let's figure out what happens when we close the valve more slowly. We'll assume that the average velocity versus time function is linear. So, L over 3a seconds after closing the valve, the wavefront traveled L over 3 from the valve to the reservoir. Let's assume that the valve opening is now at 80%. This will be the configuration of the piezometric line along the pipeline. And here it goes. Here's what happens at time equals 2L over 3A. The wavefront traveled 2L over 3 from the valve to the reservoir. Let's assume that the valve opening is now at 60%. This will be the configuration of the piezometric line along the pipeline. And here it goes. And here's what happens L over A seconds after the beginning of the closure operation. The wavefront travels L from the valve to the reservoir, and the wavefront hits the reservoir. The valve opening is now at 40%. This will be the configuration of the piezometric line along the pipeline. From now on, the reservoir will begin reflecting back the waves towards the valve, as we will see. And here it goes, and here's what happens for L over 3A seconds after the beginning of the closure operation. The valve opening is now at 20%. This will be the configuration of the piezometric line along the pipeline. Part of the pressures in the pipeline near the reservoir will be attenuated by the waves that were reflected and that are now traveling towards the valve. This happened at 1/3 of the total length. And here it goes, and here's what happens 5L over 3A seconds after the beginning of the closure operation. The valve is completely shut. This will be the configuration of the piezometric line along the pipeline. Part of the pressures in the pipeline near the reservoir will be attenuated by the waves that were reflected and that are now traveling towards the valve. This happened at 2/3 of the total length. And it keeps going. And now, notice that the waves coming from the valve can travel only 1/6 more until it reaches the opposite wave coming from the reservoir. From now on, the pressures will stop increasing in the pipeline. It's the critical situation for maximum pressures. As we can see, the waves reflected by the reservoir will attenuate the pressures along the pipeline. So, these will be the maximum transient pressures corresponding to the time closure equal to 5L over 3A. And here they are again in a cleaner representation. And these will be the minimum transient pressures. In cases like this, when we can assume that the water velocity variation is proportional to time, we can predict the maximum distance of the maximum pressure in the pipeline. This is the formula. In our example, in which the time closure was 5L over 3A, the distance of the maximum pressures was equal to L over 6, as we can see here. In the case of instantaneous closure, which means T equals 0, the distance of the maximum pressures was equal to L. All the pipeline extension will be hit by the maximum pressures. This extension will be smaller if the closure time is greater. We can predict the distance x using this formula. If the closure time is L over A, the distance will be L over 2. If the time is greater, the distance will be smaller, as we can see here. And if the closure time is equal to 2L over A, the distance will be 0. Here they are, the transient piezometric lines for this condition. The pressures can be even smaller if we close the valve even slower. But this is the subject of our next video. See you there! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.